last time, we derived the mechanical energy E equal to velocity squared minus the potential energy. And today I want to base upon this and give a little bit more interpretations and then linking that information to the orbits, the shape of the orbits. So here, we can replace the v square is equal to v dot v, and let me do a little bit of manipulations of the equation, and we can see something else. So here, if we say we take the velocity in the polar coordinate systems, then the v can be described by r squared plus r squared c theta squared. Okay. And also we're using these notations h. The magnitude of the angular momentum equal to this one. So therefore, we can rewrite v squared is simply equal to r dot squared plus h squared divided by r squared. And I'm going to rewrite the mechanical energy with this term. So therefore, mechanical energy can be described by this. Therefore, the mechanical energy can be also described by replacing the velocity, the speed square, with that term name. That can be equal to 1 half r dot square plus 1 half h r square minus mu over r. So here the purpose is I simply just want to express the energy in terms of the r and related function in the polar coordinate systems. So under these situations, you can see this is simply, right now this is described in a polar coordinate systems. And so from here, this one is, the two terms here is regarding is the potential energy. So here, why not I just give a name, and again, here is not so important. I just give a name. I call this U, okay, indicating the potential energy. So now we look at the curve, and here, from here you can see the potential energy is composed of the two terms. So we can look at here. So here again, here I want to look at is the potential energy. And the potential energy here, let me take this r, the radius from the major focus. So let me do the curve for the first one. That curve is something like this. So this curve is h. I mean, sorry, there's a typo. This should be squared. I forgot it. Okay, so I have a typo there. So that is h squared divided by r squared over 2. And then the other one, this one is decaying quicker because that is in r squared in the denominator, and this is r in the numerator, so this is the slower. So this one is negative minus mu over r. Okay, so the potential energy is simply the summation of the two terms. So let me add it up the whole things. So that is the summation of the two terms will be something like this, approaching to. Okay, so this is UR. Okay, and what we can utilize this information, yeah, we can do this one. So basically here, let me rewrite here, and so again, the mechanical energy is somehow a positive term, m plus UR. Okay, so which means, let me rewrite, so, or we can say that UR equal to E, mechanical energy minus a certain positive term. Okay, so this curve can be somehow using for interpreting this kind of information. So let me, not to overlap this one, so let me redraw that curve to here. Okay, so this is UR, let me draw it. Eventually, this curve will converge to the r-axis, which means value will become 0. Okay, this is UR here. Okay, so now with this in mind, and then I'm going to do a little bit the options for the value of E. The value of E is the mechanical energy. And mechanical energy can be positive, can be 0, can be negative. And again, what is the mechanical energy? If you remember earlier, so say if this is the Earth, this is the center of the Earth, and this is the orbit of satellites. For all the orbits centering around one celestial object, for example, the satellites about the Earth, Moon about the Earth, Earth about the Sun. Those orbits, they always corresponding to mechanical energy less than 0. Okay. And for the object that if that can go to infinity, that corresponding is mechanical energy equal to 0 or greater than 0. So here, in terms of the concept here, the mechanical energy can be negative value, can be 0, can be positive value, all the possibilities. So we can look at the possibilities for those things. The first one is this, say, let me use the different colors. The first option is, say, if we have a situation corresponding to a positive mechanical energy. So here, let me use the blue line. And let me corresponding to this value, let me call that is the value of the energy corresponding is E1, and that is positive value here. Let me here be more specific. This is 0, and this is the energy. Okay, so here I arbitrarily laid a constant positive value for E, and I denoted that value equal to E1 positive. Okay, so now for this scenario, and then we're going to look at these equations. We see what we can use. For these equations, you can see U equal to E minus this one, or how can we let me do further. Sorry, I didn't well organize. Let me do further. Okay, so this one we can see R dot square equal to, let me put that on E minus U. Okay, because this term is always positive or 0. So that means we know the relation between E and U must satisfy this equation. So we start from looking into this equation, this kind of relation to see. So the difference between E and U must be positive. So we'll look at it here. So the difference between E, the value and the mu must be always positive or 0. So that means the legible or the possible regions of motion for that object should be where? That should be here. So let me designate corresponding. This is the point where the E equal to mu, E equal to U, right? And then let me call this is saying the value corresponding is R1. So for all the value R greater than R1, that will make this relation legitimate. So this is the feasible regions of the motion the objects can achieve. If the objects want to go to any location smaller than this value R1, no, because in this way you can see U is greater than E. That will going to violate this relation. Okay, so corresponding to this, so if we have said the object. So say if we have the celestial object, for example, Earth, and say if we have a satellite or whatever the object, and that is already in space, and that object has the mechanical energy E1, which is positive. So from this information that can tell us is this. The motion of this one, the motion of these satellites around the Earth must satisfy this equation. So which means it cannot get closer, but it can go to infinity. It didn't say how far it will stop, but it will go to infinity because the region from here onward to here, every point will be the feasible positions. So that means for this one, it will have changed, and that means this one will be go to infinity. Okay, so for this case, let me designate this is corresponding. Basically, is they have a chance to go to infinity, go to this space, the deep of the space, and won't stop there. So here, corresponding is actually is a hyperbolic orbit. So here I kind of give a hyperbolic orbit. Basically, let me draw it. So say if this is the major focus, so that is something like this. So once this has passing, so the minimum distance is R1, and you won't get closer, and then it will go to infinity. For example, here this is the distance R. R can be any larger number as long as satisfy this equation. Are we okay? Okay. Then the second one, we take a second value of the energy. So now I take this value E, and actually E2 I pick up F0. Okay, so the same thing for this case, you can see the intersection here, let me call this value is R2. So that means the feasible regions of the motion is in the range of R greater than R2, right? So for the second selection project, so for the second selection object here, it has the E and mechanical energy equal to 0. So for this case, it will move in is somehow is here. It has the farther distance, which is R2, cannot be closer to R1. If this object must be closer, need to be closer to to the Earth, we need to boost his energy. So we can compare and kind of give a view. So the larger the energy, then basically this kind of the hyperbolic then would be closer to the attracting objects. Okay. So that is the reason. Again, back to that movies I mentioned to you on the first day. Again, that is the moon, and then two space shuttles launch, and then they basically take the slingshot, and in the movie scene around these positions, they approaching to the moon, and to this high speed, they begin to burn their own fuel. Hopefully, can achieve 12 G, and such that they can boost their mechanical energy, then slingshot to bring them to meet the comet there. Okay, so that is the one of the things I remember really in Van Gogh. Okay, and then the next one, I'm going to change colors, and the color is for negative. So this is the one. The third options we can choose is another value, which is E3, negative, and I code number is E3. So under these situations, and again, we have to make sure this is satisfied. So which means the value of E is always larger than the value of the U. So which means here, let me designate, this is the R3, and this is R4. So who can tell me which regions that will be feasible to an object with this energy? Which region? To make sure this one is satisfied. So that means this region, right? Only in this region, the value of E is higher than the value of U. Good? Okay, so for this case, this is E1, and this is E2, and this is E3. Then the feasible regions we're going to have is the positions of the satellites will be in between R4 and R3 based upon those symbols here. Okay? So that means this one gives us a hint is this. This is the Earth, for example, this is a satellite. And the minimum distance per our location is R3, and the maximum is R4. And basically here, this is at any point, the R can be in between R3 and R4. So that gives us a hint. This orbit should be a closed loop orbit, kind of going to do the cycling. Okay. Then the last one, I make another choice, and that is just tangent to the minimum value here. So here they just touch here. Okay. So this is E4. Again, that's still negative. So for E4, you can see corresponding here again. I make this line only touch to this point. So let me call this corresponding value is R5. So for these situations, this is the minimum. This is the minimum situations. The minimum the value of the energy we can assign. So that one corresponding is for E4 again negative. Then R, because to satisfy this equation, E must be greater than or equal to U. So that means making that feasible is R is fixed at a constant radius R5. So what this means? That means the orbit is a constant radius, which means a circular orbit. Okay? So this is a circular orbit. For this one, this is elliptic. Elliptic orbit. And for this one, E2 just match. So this is the basically the parabolic. So from here, we quickly get a kind of the first taste between the, I would say, the geometry with certain informations. And here is very kind of the high level head up for this. And so follow up here at the first time we have introduced the geometry, linking geometry with the energy things related or the conservation of the two body quantum properties. So from now on, I think the follow up is I'm going to have more detailed introductions into each of the orbits. So we will focus more on the more kind of quantitative description of those things.